All right, so like I just said, translations, it's probably, in my opinion, the easiest type of transformation because all you're doing is just sliding it. All right, you're just shifting it. All right, so most of the transformations that we're going to talk about in this class are rigid motion. There's only one of them that's not that we're going to talk about. All right. All the other ones that we're going to talk about are rigid motion. Now, just to recap what that is, rigid motion, it's where it maps lines to lines, rays to rays, segments to segments. That's just a fancy way of saying they preserve the side lengths and they preserve the angle measures of the figure. So in other words, same shape and size. What's the word for that? Congruent. Now, another name for rigid motion, so you may see this word interchangeably with rigid motion, is isometry. All right, so if you see the word isometry, that's just another name for rigid motion. All right. So, for example, if you see a question where it asks about a figure's isometry, it's asking if it's a rigid motion. Now, before we talk about the rigid motion known as a translation, we need to consider the concept of a vector. Has anyone ever heard of a vector before? So, vectors are more of a scientific term. They're mainly used in physics. All right. So, essentially, in math, we use vectors more with matrices and when we start getting into three-dimensional figures. So instead of a two-dimensional coordinate plane like x and y, it's more so when you look at the three-dimensional one of x, y, z. All right. And yeah, that is a thing. But essentially, geometric vectors are pretty simple. All it is that it's a straight line distance in a particular direction. So it's a line segment that has a designated starting point and ending point. So, for example, if we look at exercise 1 below, it says we're drawing a vector from A to B. So where you start and where you end is important because that's where the direction factor comes in. If you draw a line, that's just the distance. What you have to do is draw an arrow on that line to show the direction. So if we're starting at A, we're just going to draw a straight line to B and put an arrow. I know, so complicated. All it is showing direction. So it's saying that we're going this way instead of going this way. If I just drew a line, it's not showing me the direction I'm actually going. All right. So from E to D, start at E, go to D, Q to R, start at Q, go to R. So why do you think, let me ask you this, why do you think vectors are kind of important when it comes to translations?
Because it determines which shape was there before the transformation.
Kind of. Not necessarily, though. What does a vector actually look like? Looks like an arrow or a big geometry. A line. All right, so a line. So now let's think about the algebraic side of a line. When you think of a line in algebra, what do you think of?
A function.
A function. What type of function specifically?
Linear.
Linear. All right, what's so important about linear?
Straight.
It's like a one thing, a linear function that you always gotta know. Slope. All right. And what's true about slope? Y equals mx plus b. How do you find slope? Rise over run. Isn't that direction? Isn't that kind of translation? You're going up and over or down and over. There you have it. So, why are vectors important? Vectors actually show the slope of which a figure is traveling. All right. So, the slope of each of these vectors is actually the rule for translating. All right. So, the translation maps each point by a certain distance in a certain direction, and they all move parallel to each other because they're all going to move by the same vector. All right, so the vectors are all parallel to each other because they have the same what? Slope. So remember from math 1, parallel lines always have the same slope. All right, so you're given a vector, you use it for all the points. And that is defined as its given vector. So let's look at this next example. We're given these 3 points right here, A, B, and C, and they already graphed it for us over here. They also drew us a vector from A to A prime. All right. First off, what I want you to figure out is what did they do to go from A to A prime? The translation, obviously, but what would be a good strategy to figure it out?
Make a triangle under the vector line.
Yeah. So in other words, do rise over run. All right. So take a minute, figure out how you go from A to A prime, and write it down. Just the written rule. Thumbs up if you're ready. All right. So let's see who will be tribute today. Not here. All right, Elizabeth. What was the rule?
I don't know.
So when you did rise over run, what'd you find?
Right away. Down 3, over 6, or 5.
Yeah, that's the rule. Down 3, and then what direction to 6? So you go down 3, left and right.
Right.
Right. Good. So that's all I meant by a rule. I just wanted down 3, right 6. Or you could have said right 6, down 3. It doesn't really matter. All you had to do was just count. You go down, then over. So you're literally doing rise over run. Now, here's the fun part. The algebraic rule. All right. Now,
Oh, I was going to say,
what do you think?
x plus 6 y minus 3.
How'd you do that?
Right. So that means that x was going to go
Yep. As soon as my pen decides it wants to live, there it goes. So, right, your rule would be x plus 6, y minus 3. Now, why do you think it's x plus 6, not x minus 3? What makes that 6 go with the x?
Because it's like it's going to the right on the x-axis.
Right. And what's true about x's?
They're horizontal.
They're horizontal, which means left, right. All right. So x is horizontal. Horizontal, you can only go in two directions, to the left or to the right. Y is up, down. So that's why the down, or the minus 3, goes with the y. Now, if you actually look at the actual points, does that rule make sense? So in other words, if I look at A, so negative 3, 6, and the new point is 3, 3. Is negative 3 plus 6, 3? Yes. All right. Is 6 minus 3, 3? Yes. So our rule works. All right. And that's how you check yourself. Okay. If you can find it on the graph, all you got to do is use that, write a rule, and then check the points through the rule. Double check yourself. All right. If you don't get the exact same point, you probably did something wrong. All right. So now, take a minute, find B and C. So B prime and C prime. So find B prime and C prime and go ahead and graph it as well. So you know the rule, just use it. Thumbs up if you're ready. Okay. One more minute. Alrighty, let's go with Ayla. What'd you get for B prime?
I got 9, 5.
Yes, you are correct. So 3 plus 6 is 9. 8 minus 3 is 5. So if we graph it, it'd be about right here. So that's B prime. Now let's go with Abraham. What'd you get for C prime? 2, negative 1. Good. Negative 4 plus 6 is 2. 2 minus 3 is negative 1. So if I graphed it, it would be about right here. So if I drew the triangle, it looks exactly the same. All it did was shift. Didn't even change its orientation. Any questions on that? All right, do some more practice. So, just so you know, the general rule for writing in, the general rule for writing in arrow notation is you start with XY, maps onto, that's what this arrow means, X plus or minus A, Y plus or minus B. where A is equal to your horizontal shift. And B is your vertical shift. So in layman terms, A is left, right, B is up, down. And the negatives and positives come into play just logically, all right? If I'm talking about a horizontal number line, your left side will be what type of numbers? Negative. If I'm talking about a vertical number line, your positive numbers will be where? Vertical. 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 Up. All right? So it's just logic from there. Now, another way you can write the rule, this is called function notation, is this. Big T and little a b in the subscript. And typically it'll be A and B will either be positive or negative, and I'll tell you left, right, up, down. Or sometimes you see it as big T and then a vector AB. So these little almost look like less than greater than symbols right here, these little brackets, that's what we typically use to denote a vector. All right, so these denote a vector. All right, so what I want you guys to do, I'm going to give you a couple minutes. Try example 3 on your own. So do all of example 3. So plot the original, get the new coordinates, write it in arrow notation, and then answer the last question. right, thumbs up if you're ready. Just doing letter number 3. That's it. All right, check your answers. Zoom out a little bit. So, a couple of things. Letter E specifically. What's the difference between similar and congruent?
Congruent is exactly the same, and similar is relatively the same.
Yeah, that's pretty much the gist of it. But in geometry terms, what do you think it is? So we know congruent is same size, same shape. Does anyone know what similar is?
Same angles, different like size.
So same shape, but different size. So the angles are the same, the side lengths are not. All right. And when we get into triangles in the next unit, we'll go through like the whole properties around similar figures. But if the shape is exactly the same, it's congruent. But if it looks like it's generally the same shape, but it's just smaller or bigger, it's similar. All right. Any questions on number 3? All right, so I already saw like a lot of people starting to work through example 4, so let's just go through it together. All right. So I'm going to graph TUV real quick. All right, so 0, 3, 2, 4, 5, negative 1. So TUV. So in letter B, they gave us this rule. Can someone raise their hand and tell me in words what that rule means? Wait, right?
Left, right, down, one.
Left, right, because it's a -3. Why did I say left, right? Left 3, because it's -3. And then down 1, because it's -1. So left 3, down 1. What would be the new point? So you can either plug it into the rule or you can do it on the graph. So did anyone get the points yet? Okay, let's go, William.
-3, 2, -1, 3, 2, -2.
Good. All right, so, and I'm just going to say that those are blue. If I graph those, -3, 2, -1, 3, 2, -2. So remember to always label, because once you have multiple figures on a graph, it gets confusing if you don't label. U prime, V prime. Now, they then asked us to take the figure that we just found and do another rule to it. So this is where those double primes come in. Like I said, double prime just means we have done 2 transformations since the original figure. All right, that's all it means. So for every prime, that's 1 transformation done to the original. All right. So what's the rule for E in words? What is it? Right 3 and down 3. So what would the new points be? Let's go, Riley. Okay, slow down. Say that one more time.
0, -1, 2, 0, 5, -5.
Good. All right, so if I graph that very quickly, got 0, -1, 2, 0, 5, -5. So T double prime, U double prime, V double prime. So here's the question. If I'm going from black to purple, are they congruent figures? Yeah. So all we did was two translations. We know translations are rigid motions. All right. So yes, they are congruent. So what we just did is we did what we call a composition of transformations. And composition is just a big word meaning more than one. So when you get to Math 3, you'll see composite functions, all right? You're basically doing one function within another function, all right? Here, you're doing one transformation and then another transformation, all right? So if I wanted to write a rule to just describe if I went from the original to the final, so to the double primes, what would it be? So in words, what would it be? It'd be down 4. Did I graph that on the wrong line? No, I didn't. So it'd be down 4, and then it actually didn't shift right or left from the original. It went back to its original setting. So all it did was that it went down 4. So in arrow notation, it would be just x, because we're subtracting 0, and then y minus 4. So if you just see the variable by itself, it just means it stays where it is, or it doesn't change. Any questions on translation? Not too bad, right? We're starting out easy. All right. Okay, so your homework for tonight is pages 7 and 8. I will check it Monday. Now, before you get into your homework, I want to go through my Canvas page real quick just so I can explain how to navigate it. Just in case, I doubt it's going to happen anymore, but, there's been talk about snow Monday, and there's been rumors of remote day. But, again, it's not looking like it, but I just want to cover my bases just in case. All right? So, if you go to my Canvas page, just give me 1 second.